Okay, so this is joint with Elchanan Mossel at MIT, Manuel Mueller-Frank at the Business School in Barcelona and University of Navarre, and Allan Slide, Princeton. Okay, so just quickly, what is social learning? Maybe I can skip most of the slide. I think we know what social learning is. What I do want to point out, is there a laser pointer here? Oh, yeah, so what I do want to point out that the sort of questions that people ask are what happens after a long time. So we have some kind of process that people participate in, and the sort of questions that people ask is what happens after a long time. And two typical questions are agreement. Do people end up agreeing on whatever it is that they're learning? Or can you get different opinions sustained for arbitrarily long? And learning. Do people actually learn this thing that they're exchanging information about? There are all sorts of approaches to this. I'm going to focus on a completely rational expected utility maximizing approach. So I guess more along the lines of Krishna than Jerry. Okay. So what I'm going to do, I'm going to give you some examples to have in mind of rational social learning models. And then I'm going to try and introduce a framework that is very, very general, encompasses all of these, and somehow gives you a new way to look at these models and prove things about a very, very large class of models. And these are what we call social learning equilibria. Okay, this might be a bit mysterious at this moment, but bear with me. So here's just a very classical, the sequential herding model of Chandani, Hirschleifer, and Welch. So another paper by Banerjee that's very similar. And I'm guessing probably most people here know it, but I'll go through it very quickly. There are two new restaurants open on campus, and you don't know which one is better. Everybody gets a private signal. Now people are queuing outside the restaurant. Each time each person chooses one of them to go to, and everybody else sees their choice. And this beautiful result that they have, this herding result, is that from some point on, everybody's going to do the same thing. So at some point, when you've seen 100 people go to restaurant A, you're also going to go to restaurant A no matter what your private signal is, and now everybody does the same thing from some point on. And so this is usually called herd behavior. I want to think of this as agreement. So what's another way of phrasing what's happening here is we have this infinite long line of people, except for some finite number in the beginning, everybody does the same thing. So we end up in a state at the end of the game where almost everybody agrees that this option is better than that option. In terms of learning, there's this distinction that I won't explain between bounded and unbounded signals. When signals are bounded, almost everybody, this co-finite set of people that does the same thing, doesn't necessarily do the correct thing. When signals are unbounded, it turns out there's still a co-finite set that does the same thing. You still have agreement, but now they're going to agree on the correct action. Okay, so sometimes you have learning in this model, and sometimes you don't. Here's another model. I don't know that this appears in any particular paper. Now I'm going to have a large finite group of agents, and I'm going to have time periods. Each one of them is going to get a signal at time 0 and no more signals. Imagine that they have to make a binary choice in each time period. So say I have to decide every day at lunch whether to eat my bread with butter or margarine, and I don't know which one is healthier. It's the same choice for everybody. We all get private signals in the beginning. Then every day we go to lunch together. I choose butter or margarine, and I see what everybody else chose. Okay, so this is a different social learning game. And you can ask the same questions. Agreement, do we all choose the same either butter or margarine eventually, at the limit or in some sense? And do we learn? So somehow we all started out with these private signals. Is this information aggregated? So maybe when the group is very, very large, do we all eventually do the correct thing at the end? Okay, so this is another very, very different social learning model. And what I want to do is I want to look at a very, very general framework that includes both of these models in one single framework. And that's going to be the following. It's going to have three components: a setting, an extensive form, and a notion of equilibrium. The setting is two states of the world, two actions. My utility is I have to take an action and there's a state. My utility for an action and a state is just one if I matched it in 0 otherwise. I'm going to look at a countably infinite group of agents. So all the results that I tell you, they hold for large finite groups with an additional layer of quantifiers and epsilons and deltas. So I'll just make the statements cleaner and just talk about a countable infinite group. But everything really is just about the group being large. So we're going to focus on that case. We're going to choose our state at random, and then everybody's going to get informative independent private signals. So this is common to both the herding model and this repeated butter margarine model. What differs between the butter margarine model and the two restaurant model is the extensive form. What is the dynamics? Who chooses what action when? And the extensive form, we're going to look at a very general class of extensive forms that encompasses both of these. So for each agent, there's going to be a set of action periods. So these are the periods in which this agent has to choose an action. In the sequential model, agent n only acts at a time n. In the repeated model, every agent acts at every time period. I'm saying, okay, just generally, each agent acts in some subset of the time periods. And each agent, before acting, observes something. And I'm leaving this very, very general. Something that's a function of other people's previous actions, private signals. It could be anything. So again, in the sequential model, I observed the actions of the people who came before me. In the repeated model that I gave, I observed all the actions of all the people who came before me. But maybe I also talk to the person who's sitting next to me, and I text my grandmother who's behind me in line for the restaurant. And maybe, I don't know what. You can imagine all sorts of ways that I could get information before taking each one of my actions. And as usual, we're going to have a discount factor, and we're going to have a strategy which tells me how to choose my actions as a function of what I've observed so far. And this defines a game. And this game could be hard to think about, so if you want to make your life maybe easier, just imagine that agents are myopic, so they do this based on everything they've observed. They calculate which is more likely to be the better action and just choose that one without any strategic considerations. This will also hold for that case. But for the strategic case, the solution concept is a Nash equilibrium, so we just look at a strategy profile where nobody can improve their sum of discounted utilities. Okay, any questions about that? This is I gave this talk that's an hour long, and I was going to throw out some slides, but I decided to just leave them all and speak faster. So it's okay. So and I should say that there are many, many other models that have been studied in the literature that fall under this very, very general framework. So there's a problem with this framework. The problem is we really only know how to analyze these sort of models when the extensive form is very, very simple, like in this sequential restaurant game. Even in this margarine butter game, I don't know how to analyze this game. I don't know how to say anything about its equilibria. Well, okay, I'll tell you some things in a minute. But a priori, I didn't know how to analyze its equilibria. It's very difficult to figure out what people's beliefs are after, okay, I saw Joe eating butter, but then Jane ate margarine, so Joe changed. So I have to make all these crazy inferences. It's very hard to, it's not tractable. You can't write down people's beliefs. I think that there's a recent result from some people here. It's NP hard to actually calculate what the correct thing to do. So what we do is we really limit ourselves to these very, very simple stylized models. And we hope that if we had to make the model more complicated, the results would still hold. So if I'm not just standing in line exactly seeing who entered before me, but I'm also texting my grandmother who's already inside, and I'm talking to the person this, and I'm paying somebody to tell me what they think. I don't know. Maybe the results would be very different. We don't know. We can't analyze all these other models. So, this is, I guess, the general problem with economics or modeling, right? You don't know how your assumptions, but with these dynamic things, it's very, very hard to understand how making small changes in the model affects what happens after a long, long time. So, I'm going to solve this problem. So here's what we do. Okay, not really, but I'm going to try and solve this problem. And I'm going to introduce something that's called a social learning equilibrium. And this is just going to be a static concept. I'm going to get rid of the extensive form. And I'm just going to look at a static equilibrium concept. And what this equilibrium concept will try to capture is what happens at time infinity at the end of some extensive form of some game. Okay, so instead of analyzing exactly what happens in every period of this butter margarine game and what I do and how I make inferences, I just look at what happens at time infinity. And I try to model that directly without looking at the extensive form. And it turns out that you can, it makes things easier to analyze. And you can say very easily what happens at time infinity in a way that is agnostic to many, many changes in the extensive form. So now I can take a huge class of extensive forms, and I don't really care about most of the details. I can tell you what happens at time infinity just by analyzing this equilibrium at time infinity. This is close in spirit to what's called the rational expectations equilibrium. So basically, I guess it's not a new solution concept in game theory. We're taking rational expectations equilibria and adapting them to the social learning setting in some sense. Okay, so here's the actual model. We're going to have a social learning setting that's just like before, 2 states, 2 actions, IID signals. Now, instead of talking about an extensive form, we're not going to have an extensive form. We're just going to have something that each person knows. So each person is going to know her own private signal, and in addition, something, Li. I'm allowing this, at least in the beginning, I'm allowing this to be anything. And the way I'm thinking about them is that this is what I've learned through participating in some game. So these Li's model all the information that I've gathered by all the observations I've made throughout this game. But I don't really care about the game. I just keep everything that I've learned in the game. And now each person is going to choose an action, and they're going to get a utility that's just like before, 1 if the action matches the state, and otherwise. And the equilibrium condition is very, very simple. It just says whatever action I choose is optimal. It maximizes my expected utility given what I know. Okay? So you can forget about the whole extensive form and just look at this as a mathematical object on its own. It doesn't include the extensive form. I do want to model it as capturing what happens at time infinity, but I've really lost all that. All it is a group of agents who each know something, each do something, and each is optimizing, each is happy to do what they're doing given what they know. So each agent knows Si and Li, each agent chooses an action AI, and each person just chooses an action that maximizes their expected utility given what they know. This is a very, very simple definition. Okay? So the first theorem is this. Well, it's not due to us. It's basically a rephrasing of a theorem for a very nice paper by Rosenberg, Sola, and VA from 2009. And by the way, the social learning equilibrium, I'm abbreviating it as SLE. And here's what the first theorem says. I'm going to have some extensive form in which in each action period I learn some information LIT and I take an action AIT. I'm going to fix some Nash equilibrium, and I'm going to say that Li is what I learned throughout the game, what agent I learned throughout the game, and AI is the limit of the sequence of actions that I took, and if it doesn't have a limit, just choose any limit point. The theorem says this is a social learning equilibrium. What this theorem says is in any of these social learning models, we converge in the end to a social learning equilibrium. We converge to a state where everybody's doing the optimal thing given what they know. Okay? So now what this theorem is important is it says if you want to know what happens at time infinity, you can forget about the extensive form. The extensive form converges to something like this, and you can analyze directly what happens at time infinity. Okay, so I'm not going to have time, but I'm going to say that an SLE satisfies agreement if there's a random action A0 that all players choose. Right? So social learning equilibrium is a pair. What everybody knows, this is a vector of these LIs that everybody knows, and this is a vector of AIs of what everybody does. I'm going to say that we have agreement in the social learning equilibrium if what everybody does is always the same. It could be random, it doesn't have to be constant, but it's always the same between people. And I'm going to say that it satisfies herding if almost everybody does the same thing, everybody except a finite set. And I'm going to say that it's aggregating if this thing that we're doing is the correct thing with probability 1. So here's almost our first results. I'm going to look at what I'm going to call a complete social learning equilibrium. You should think of complete as in a complete network. In a complete social learning equilibrium, part of what everybody knows, this is what person I knows, they know some information, and in addition, they know what everybody else does. So for example, in this margarine butter game, because we observe everybody's actions, we know what everybody converged to. So imagine in a complete social learning equilibrium, we have a group of people. Everybody has some information, which includes what everybody else does, and everybody's happy doing what they're doing. Okay, so you can forget now about the extensive form. This butter margarine game is going to converge to this, but you can forget about that. Many, many other games are going to converge to this. But now take any equilibrium where, given what I know, I'm happy what I'm doing, and part of what I know is what everybody else does. So here's the theorem. Every such equilibrium satisfies agreement. If we're all happy doing what we're doing, and we all know what everybody else is doing, we have to all be doing the same thing. Okay? And, okay, I don't have time to tell you much about the proof of this, but this crucially uses the fact that the group is large. So for large finite groups, this holds with probability 1 minus epsilon for large enough n. So for finite groups, it is possible that we disagree, but as the group gets larger, the probability that we agree has to go to 0. The probability that we disagree has to go to 0. The proof of this uses something that we call the concentration of dependence principle. So this concentration of dependence, and actually all our proofs use this. This is what is the basis of the entire paper. This is just a mathematical lemma, I would call it. It's not a new one. It's somehow very basic for people in probability or in ergodic theory. But I think it has surprising interpretations in the social learning setting. So this is the lemma. I'm going to have IID random variables, and I'm going to have B. B is any event in my probability space that has also these random variables. And I'm going to say that this B is epsilon independent of a particular xi if for any event A that depends only on xi, it holds that the probability of the intersection of A and B is very close up to epsilon to the product of the probabilities. So actually, if this was equal to that, if the difference was 0, this would just mean that B is independent of xi. Okay, it's almost independent, up to epsilon. So the lemma says the following. Except for at most 1 over epsilon squared, it doesn't matter that it's 1 over epsilon, except for at most some finite number of i's, each xi is epsilon independent of B. So it doesn't matter what this event B is. So here's another way of phrasing this. Imagine that we have a group of agents. Each one of them gets an independent signal, and they all have to decide whether to take this action or that action. And this is just going to be some function of their signals. Then this decision is epsilon independent of almost all the signals. No matter how it is that as a group we decide to do something, that's a function of our private signals. There's really 7 people in DC who are making the decision, and everybody else's signal is practically independent. Okay? So, yeah, unfortunately I don't have time to explain why this is at the basis of the proofs, but it turns out to be a powerful tool in this framework. So here's our next theorem, and it says that when signals are unbounded, every social learning equilibrium that satisfies agreement is aggregating. Because let me parse that for you. Take any social learning equilibrium where we all do the same thing. So we're all happy to do what we're doing, and we're all doing the same thing. When signals are unbounded, we have to be doing the correct thing. It's impossible for us to agree on the wrong thing. So somehow it doesn't matter how we got to this state. It doesn't matter what the extensive form game is of the game that we played. As long as the end result is that we all agree, we have to agree on the correct thing. It's impossible to reach agreement without exchanging enough information to reach agreement on the correct thing. And this is completely independent of the extensive form of the game. So now you can imagine that I don't choose margarine butter every day and see exactly what I do, but I also talk to my friend and don't come some days because I'm sick and this, who knows, I don't care. In all these cases, we'll reach agreement in the end, and therefore if signals are unbounded, it'll be aggregating. Am I out of time? Yeah. So that's what I have time for. Thank you. The discount factor it doesn't appear in the social learning equilibrium. Social learning equilibrium is what happens at time infinity. You just choose one action. Sorry? The theorem that tells you the theorem that tells you that any equilibrium of any of these games converges to a social learning equilibrium holds for any discount factor. Whatever the discount factor is, you converge to a social learning equilibrium. Yeah. For bounded signals, you can agree on the wrong thing. Yes. So it's easy to construct an example. Yeah.
Thanks for speaking.
Thank you.